Okay, so the subject of chapter 15 is thermodynamics. So the great development of thermodynamics started back then during the Industrial Revolution. And why is that? What is the main topic, the main discussion in thermodynamics? Well, in chapter 14 we talked about heat. We said that heat is energy that is transferred from one object to another one because of a difference in temperature. So this energy that is transferred because one object is hotter than the other one. So energy that is transferred so that this system will reach equilibrium, will reach a common average temperature. Okay, now here we are. We have heat being transferred. Now we have energy being transferred from one point to the other. What do we want to do now? We want to use this energy that is being transferred from one point to the other to get work done. So that's the main topic of the Industrial Revolution, right? We want to use energy to get our train moving, to get a machine to do the work that we want to get done. Okay. All right. So we are going to start discussing the first law of thermodynamics, and the first law of thermodynamics is related to this concept that we already talked about, internal energy. So remember what we said about internal energy back in chapter 14. We said that internal energy is the total energy of all the molecules in the object. Which energy? Kinetic energy. So the internal energy is N, and is the number of all the molecules in the object multiplied by the average kinetic energy of each one of these molecules. So the total energy, the internal energy is N multiplied by this average kinetic energy. But remember that back in chapter 13, we said that kinetic energy, the average kinetic energy, is related to the temperature of the system. So we can also write this internal energy as 3/2 of N, number of moles, R, the universal constant, and T, temperature. Okay, so this is the U. What we are going to talk about in chapter 15, in the first law of thermodynamics, is the delta U. Okay, so let's write here, U is 3/2 of nRT. And we are going to use a lot of this equation in this chapter. But the first law is about the change in U. So in other words, it is about the change in temperature. Okay, so how do we get this temperature of the system to be changed? In other words, how do we get the internal energy to be changed? So we see in this equation here, delta U, the change in internal energy in a system that is closed, is equal to what? The energy that is added to the system, the Q. The energy that is being added to the system, this energy that is being transferred to the system. So it's equal to Q. Okay, so if I inject energy in the system, I can understand why the temperature is going to change, increase. But you also see that this change in internal energy is Q minus this W. This W is the work done by the system. Now, so we can understand this equation. It's very intuitive. This is the energy that is added to the system. Q is the energy being added to the system. So we have our delta T will increase because of Q. But if the system uses part of this energy to do work, well, it will lose part of this energy, so that delta T will decrease. Okay, so it's the competition between these two. Okay, now very important comment here. Be very careful with the sign. We are going to be using this minus sign here if the work is done by the system. So the system is using part of this energy, so it's losing part of this energy that was injected. So we use this minus if the work is done by. So Q minus work if the energy is done by the system. Okay? If the work is done to the system, then this will be Q plus W. Let's organize this. We are saying that we'll have Q minus W if the work is done And let's put now this in red. By the system. Okay. Now, if the work is done to the system, we put plus. So this is work done to the system. We can understand why we have to put this plus sign, because if the work is done on the system, that means we are injecting energy also through the work. And so the idea is, for example, suppose I have a certain recipient. I'm injecting Q, I'm injecting energy, and on top of that, with my hands, I am shrinking this recipient, so I'm doing work on this recipient. So I'm adding energy through heat, and I'm also adding energy by doing work on it. Okay, but if it's the system itself that is doing work, then it would be losing energy. Okay. Okay, so in some other comments here that you see in the text is how we call these variables. Now, if U, the internal energy, V, which is volume, P, which is pressure, T, temperature, mass, and the number of moles, these are all quantities associated with a specific state of the system. At this state, at this point, this system has this many moles, this specific temperature, this pressure, and so on. So we call these quantities state variables. On the other hand, Q, heat, and W, work, they are not state variables because they are associated with a change in the system. We have Q is the energy that is being transferred to the system or out of the system. So we have this transfer of energy. And what is work? Work is force multiplied by displacement. So they all associated with changes, not a specific fixed point, specific state. All right? Okay, so let's just solve this simple problem here just to make sure that these ideas about the first law were understood. What does the problem say? That we have 2500 joules of heat added to the system. Okay, so this Q here is positive, is being added to the system. And we also have 1800 joules of work done on the system. So it's more energy that we're injecting the system now through work. So we have this work done on the system, 18 joule. So, and now the question is, what is the change in internal energy, the delta U? Well, heat plus work, correct? Because it's work done on the system. So both are being added, 2500 plus 1800, and that's why we see the answer there, 4300 joules. Okay, so it's a simple problem, but it's just to emphasize the idea that this is heat plus work because this work is done on the system. So this is the end of this beginning of chapter 15.